Hello and welcome. Today we're going to look at an enrichment lecture or lesson, an alternative to the Weierstrass substitutions. This is like basically the substitution with the little t identities when the half tan identity, where we're using t is equal to the tan of x over 2, etc., etc. This is in further maths these days, I believe, in most boards. And I'm going to show you an alternative which does not actually involve directly using this particular substitution, but it involves some kind of manipulation. So I'm going to show a few examples. Today I'm feeling very lazy. I don't want to be standing in front of the board, so I'm going to do it on my desk, and hopefully you'll enjoy it just as much. Okay, so let's start with the first example. We have the integral from 0 to 2 pi over 3, and we have 1 over 5 plus 4 lots of the cos of x dx. And of course, this is very standard. You can do it, of course, with this particular type of substitution, but we're going to manipulate it. And this is how we manipulate this. This is equal to limits, of course, 0 to 2 pi over 3. And my intention is to create half angles with the existing quantities I have on my denominator. So 5 plus 4, I'm going to use the double angle. So I'm going to treat that as being a double angle, the cos of 2 lots of x over 2. So that will give me 2 lots of cos squared of x over 2 minus 1. Standard trig identity from straight maths. So that is 1 over this. And of course, the next thing is just to tidy. And what are we getting? 0 to 2 pi over 3 multiplied out. I'm going to put the cos bit first. So it's going to be an 8 lots of cos squared of x over 2. And 5 take away 4 is plus 1 and 1 on the denominator. This is my intention now. My intention whenever I do this type of manipulations is to create an integral which looks something like that. We're going to have a sec squared of x over 2 at the top and a function of tan of x over 2 at the denominator. Okay, so it might be constants, of course, there, but that doesn't really matter. The way I'm going to do this particular one, you can think of it from this line to the next as either I'm going to divide top and bottom, all three terms, by cos squared of x over 2, or multiplying everything by sec squared of x over 2. Whichever way you see it, I see a mix of that when I do normally this type of question. So that's equal to 0 to 2 pi over 3. And the limits don't change in any way because we're not using a substitution, of course. So this will become a sec squared of x over 2. This will be turned into an 8. And this, of course, will become a sec squared of x over 2 dx. Okay, I have the sec squared, of course. I create that first, but I don't have the function of my tan. Well, there is a tan in there, of course, because I can use, of course, the standard identity. 1 plus tan squared is equal to sec squared of the same argument. Limits 0 to 2 pi over 3. And nothing happening on the top, just merely recopying it. Sec squared of x over 2. And this will now be 8. And probably you let me to write that straight away into a 9. I'm going to rub off this 8. Actually, let's rub it together. So there's a 1 plus tan squared from there. So it's going to be a 9 plus the tan squared of x over 2. And I managed, of course, to get my integral into this particular form, which is now will allow me, let me just get that out of the way, to actually do it by recognition. All right. So if we look at this particular integral, this something which looks like that comes from differentiating an arctan. I hope you can see it. This will integrate. I'm going to sort out constants. I'm going to put the evaluation brackets. So I have an arctan, and this requires its enrichment now. I wouldn't advise you to be doing things like that on your exam unless you're showing off and you like to play dangerously. So this is the arctan of the tan of x over 2, the whole thing over 3. Where's that is coming from? This is a standard form. Is, of course, I hope you remember your standard du, and then if you have u squared plus a squared is, of course, 1 over a arctan of u over a. So at the moment, this is because it's 3 squared, so that's your constant, and this is the bit that is inside the arctan, because of course now it's going to go to 1 over, but it will also produce the differential of that is something which looks like that. So if we go to now to finish off the little bits that we need in there, of course we need that 1 over a, so there's going to be a third in front of it. That's the 1 over a in there. And when we differentiate now the tan of x over 2, there's extra bits to be created in there. Is this will also produce a half lots of this. So we need to get rid of that half. So we need to divide 1 divided by half. So that will be in fact a times 2. It doesn't really matter. Let me just put it here. 2 times a third. Limits 0 to 2 pi over 3. And now I can finish off my question. I just need to just put my numbers and I'm done. So this is equal to 2/3. Now the arctan, 2 pi over 3, 120 divided by 2 is 60. Tan of 60 is √3. So this is the arctan of, what did I say? I lost it now. Let's start again. That was 120 divided by 2 is 60. The tan of 60 is √3. So that's √3 over 3. So that's the arctan of √3 over 3, which is a nice number, minus, we're putting 0 in there. So if we're putting 0, the whole thing will become 0. The arctan of 0 is 0. I don't even know why I'm bothering to write it. And therefore, now the final answer will be 2/3 times the arctan of √3 over 3. Of your calculator, of course, it will be pi over 630 degrees. And this will give me pi over 9. I hope it's all correct and I haven't made any silly errors. Okay, so I hope you follow this one. So that was example number 1. Let's look at another example to just master this particular manipulation. As I said, an alternative. It's useful to know. It helps you with your recognitions of integrals, which is a very important skill in higher level integration. Okay, the second integral that I've got on the list is another one that, of course, that's the standard method. I've taken all this from exams in the last 10 years where it was actually suggested that you use the substitution. For example, x is equal to, or t rather, is equal to the tan. I'm saying x and I'm writing tan. What the hell is happening to me? Okay, let's wrap it off. I'm getting very absent-minded. It's a little bit late in the day. Maybe I should go to bed. 2 minus cos x. I don't even remember what I was saying just before my train of thought was interrupted. So this is the integral now. 0 to pi over 2, 1 over 2 minus the cos of x dx. And I'm not going to use the little t identities or little t substitution. All right, this is how I manipulate. I still need half angles. So 0 to pi over 2. Let's leave that 2 as he is for the time being and switch this into some half angles. The cos, of course, I have the choice of cos or sines. I'm going to go for cos again. If you get it the wrong way around, if you put the sine, you realize later it doesn't quite work, you can just go back to the step and just change it. So that's going to be 2 cos squared of x over 2 minus 1, there's a 1 there, dx. Quick tidy, 0 to pi over 2. What are we going to get in there? We're getting 2 minus 1, which is a 3, minus 2 lots of the cos squared of x over 2 and a 1 on the top. Okay, I want to create, of course, my sec squared. That's the kind of sequence that I should have in my head. A sec squared of this argument on the top. So we do that very, very quickly by multiplying top and bottom by sec squared of x over 2, or dividing by this. Is exactly the same thing. 0 to pi over 2 on the top, sec squared of x over 2, and this will now change. This will become a 3 sec squared of x over 2, and this will clear to just the coefficient of 2 dx. We have now the correct thing on the top, but now with the function of tangent at the bottom. Of course, we're going to swap that using the identity 1 plus tan squared of some argument is equal to the sec squared of the same argument. So 3, this is all straight maths. Sec is now 1 plus tan squared of x over 2 minus a 2. and I have a sec squared of x over 2 on the numerator. Quick tidy, I forgot the limits there, 0 to pi over 2. So let's start with the limits so we don't forget them. And what happens now here? The number bits, 3 minus 2, I've got 1 plus 3 lots of tan squared of x over 2, and then we got the sec squared of x over 2 dx. Is this an arctan like in the previous example? The answer is yes, it is, but we need to kind of like tidy a little bit the bits. We don't have quite the way we want them. We want basically a 1 in there and any number to go to the other side. So the way we'll do that is we can either factorize or divide, whichever way you prefer to see it as. I'm going to pull a third outside the integral. That's probably the better way of doing this. 0 to pi over 2. So the 3 was pulled out of the denominator. And then I'm going to write this bit first. So it's going to be now the tan squared of x over 2. And this quantity now is plus 1/3, which I'm going to write it as 1 over the square root of 3 all squared, because I want it to be ready in the form to integrate into an arctan. Okay, so this is now the difficult bit, is to actually reverse this integration. And I do remind you again, this is enrichment, is for people that want that little bit extra with the integration. Okay, this is the arctan of some sort. So first of all, the 1/3, which is on the outside, is the arctan of what? It's the arctan of the tan of x over 2 divided by 1 over root 3. Let me actually write it. 1 over the square root of 3. And of course, at the front, I will also have a 1 over the 1 over a in the standard formula that you are familiar in the formula book that is given in exams. So that's this bit here. It will also produce a times a half for when I come to differentiate the argument of the x over 2. And of course, I have to take care of that. So 1 divided by 1/2 is another thing. I would have written straight away, of course, as a 2. So I claim this differentiates to exactly what I have in there. So you can check it yourself or try to follow. I don't want to use another substitution. The whole point of doing this in this particular fashion is we have really super heavy weights now, and substitution is like for the weak, it's not for us. So we're very strong. So let's tidy this up. We have, first of all, a root 3 was going to come to the top. So this is equal to 2 root 3. That's from these two bits here. 2 root 3 divided by 3. That's this bit here. And now we have, of course, the arctan of the x over 2. Oops, I should have really written that differently as well, because that's 1 over root 3. So we can write it, the arctan of the square root of 3 tan of x over 2. And we have evaluation. I can put the brackets here, probably it's easier, but let's keep the whole thing inside to keep him warm. All right, time to now start the evaluation with all of this. Let's see what we are getting at the end of all this integration. Putting pi over 2, first of all, in there. Let's write the 2 root 3 over 3. Pi over 2, 90/45. Tan of 45 is 1. So that's the arctan of root 3, which is a good number. Minus, we're putting 0. Tan of 0 is 0. Arctan of 0 is 0. And therefore, the answer for this one is 2 root 3 over 3. Arctan of square root of 3 is 60 degrees. So that's pi over 3. And I make this not a very nice number. It's got all sorts of ugly things all bunched up together. It's a 2 pi root 3 over 9. I hope it's all good there. Okay, so that was example number 2. We'll go to example number 3. And the question, of course, is, do these things always go to arctans? Because the first 2 examples we've done, they eventually had to recognize arctans. The answer is no, but arctans are very common in this type of integrals. We'll see, I think, maybe I'll do 1 or 2 more where it doesn't go to arctan. This can be quite involved, by the way. So integral number 3. This looks quite nice in appearance. I have the answer to that particular one as 1. I have the questions and the answers. I don't have the workings in between, but to me that looks very pleasant in appearance. So it's 0 to pi over 2, and we have 1 over 1 plus the sine of x. This can be done in other ways as well, this particular one. Different to how I'm going to show you now, and also different to using the little t identities, but we're going to do it with the same theme that we're using in this particular lesson. So and apparently the final answer to that is 1. So I doubt if that's an arctan, because of course if you integrate to arctans we'll get something pi in all of this. So let's start with the standard setup, 0 to pi over 2. We can do that a little bit differently as well. We can actually write this as cos squared. I don't know if that makes sense. I don't want to write it down, or shall I just do it in this particular fashion? This one, it's a variant. It's only because I got a 1 in there, so I can actually do it a little bit differently to have done the previous two. Yes, let me just do it a slightly different way, but the final objective is exactly the same. So I'm going to write this as cos squared of x over 2 plus sine squared of x over 2. That's of course my 1. I'm moving into half angles, and this of course is a plus 2 sine of x over 2 cos x over 2. So I'm treating the x as being 2 lots of x over 2. And the top is 1. What am I trying to do in all of this? First of all, create a sec squared of x over 2 to the top. All right, how are we going to do that? Exactly the same way we've done the previous two. So 0 to pi over 2. Multiply top and bottom by sec squared of x over 2, or divide by the cos squared of x over 2. Dividing this by cos squared of x over 2, it'll give me 1. Dividing this by cos squared of x over 2, it'll give me tan squared of x over 2. Dividing this by cos squared of x over 2, it will cancel this cos, and then it's going to leave me sine over cos. So it's plus 2 lots of tan, not squared. So here I got tan squared, but here I have a tan of x and dx. I've achieved what I need to achieve. I have a function of tan of x over 2 here, and a sec squared, of course, on the numerator. So how does that help me? Because of course the differential of a tan is something which looks like that. If we look closely at this, this is a perfect square. I don't know if we can all see it. 0 to pi over 2. Let me just write it and then we can check it backwards. So that is the tan of x over 2 plus 1 all squared with a sec squared of x over 2 dx. There's my tan squared, there's multiplied together and double, and there's my 1 squared there. So this is an easy integral to do. I hope you can see, if I had a 1 over x squared, just a very simple integral dx, the answer to that would have been minus 1 over x plus a constant. It works exactly the same way where my x is all of this, but of course here this needs to be there because of course the chain will produce something which looks like that. I hope you can see what I'm referring to. So I'm integrating that now by recognition. So I'm making it minus tan of x over 2 plus 1. And I just want to check first of all what other bits are there. I'm leaving that just in case. It's a 1 for the time being, but when I differentiate that, it will also produce a half sec squared of x over 2. Of course, that should be there because that's the whole point of all of this. So we've got another half. So 1 divided by half, of course, we need to have in there a 2. So I'm going to write it there rather than writing a 1 and then putting 1 divided by half. So that's all there is to it. 0 and pi over 2. And let's clear the board because this is in our feet. And also, if you let me, I'm going to do it on this line. I'm not going to write it again. Let's swap the limits so we can make that into a plus and swap the limits, 0 there and pi over 2. It'll be easier in this evaluation. So what happens now when we're putting our limits in? The tan of 0 is of course in this particular case a 1. So we got a 2. What's happening in there? We got 2 over tan of 0 is 0. 2 over 1 for the top limit. minus pi over 2. The pi over 2 needs to go in here. So it's 90, 45. Tan of 45 is, of course, 1. Plus 1 is 2, so that's 2 over 2. So, of course, the answer is 2 minus 1, which, of course, is 1, which is what I said this integral should go to at the very end. I think we have just about enough time maybe to squeeze a fourth one. That looks a little bit long. It's got quite a few bits on the denominator. I wonder if the lecture is going to get a little bit too long. Let's risk it and let's try to do one more example in all of this. All right, this is now the integral from 0 to pi over 2, 1 plus sine x plus the cos of x with a 1 on the top dx. You're going to have to excuse me for a second. I'm going to get off the chair just to check that, because I did move my board a little bit, and I hope he's still in focus and you can see what I'm writing. Okay, it still looks to be okay. So let's proceed now in doing this particular integral. This is very, very messy because we got a sine and a cos. The plan is exactly the same. So integral 0 to pi over 2. Create, first of all, in this particular example, half angles. That's always the first step. This one is going to be a sine of 2a. So it's going to be 2 sine of x over 2 cos of x over 2. That's this bit here. And for this one, do you use a sine or do we use a cos? Let me just think what's the best one to use for this particular one. As I said earlier on, if you can't see which one out of the two double angle for cos you either need the cos squared or the sine squared one. Just go for one of them, and if it doesn't work, go back and change it. I think I can just about see I need, I didn't leave enough room there, 2 cos squared of x over 2 minus 1. That's the one that we need for this particular integral. Okay, tidy time. So let's equal. This we're going to have to, this looks very, very messy and it might take a little bit longer than I anticipated. So we have 1 plus 2 sine of x over 2 cos of x over 2, and then we have plus 4 cos squared of x over 2 minus 2, and we have a 1 on the top. Okay, dx. Rather than just rubbing off, let's tidy as we have it in there. Let's write the 4 cos squared of x over 2 first, plus 2 lots of sine x over 2 cos of x over 2, and then we have a minus 1 in all of this. Okay, next step is, of course, to create the sec squared on the top dx equal. We see now in the fourth example, I'm not going to explain exactly the same things. Sec squared of x over 2. This will become a 4. This will become cos goes, that creates a tan, 2 tan of x over 2 minus a sec squared of x over 2 dx. And I'm going to go one more line, hopefully still visible on the video. I keep forgetting the limits. Pi over 2, pi over 2. And 0 to pi over 2. And the last thing I need to do is to put 4 plus 2 tan of x over 2. That's, of course, the denominator. And this is going to be minus bracket sec. Now it's going to go 1 plus tan squared of x over 2. It's not difficult. It's the key thing with that, the manipulations in the beginning, once you understand what is needed really, the kind of routine. The difficult bits, if you're doing this type of work, is basically once you get to the almost the penultimate step, is to actually see the kind of the reverse chain rule. Okay, so arctans can sometimes be difficult. This one, I have no idea what will happen to it. So let's create some space, and let's look now at the tidy of this expression. Let's switch into a thinner pen as well. Writing in a thin pen. All my work, I'm using this particular type of pens for my work. I've been using them for God knows how long, 30 years now. The Pilots, I think it's called CG Tech 4 or something like that. I call them my thinking pens because when I write in very, very thin, it helps me concentrate. So this is a thin version of a dry marker. So it's no plug intended, by the way, yeah. So it's 0 to pi over 2. And what will happen now at the bottom? Careful, because this is not a tan squared. I was about to put them together. I've got in there it's just a total mess. The signs are all over the place. 4 minus 1. So first of all, a 3. Plus 2 tan of x over 2. That's this bit here. And then I go a minus tan squared of x over 2. And on the top, of course, I've got a sec squared of x over 2. This is not nice. It's not nice at all. So need to think now what to do next. What's the best plan for the next line? The next plan for me would have been probably, I like to make this positive because some kind of completing of the square in here, isn't it? He said we got the tan square, we got the 2, and we need to borrow 1, but I can't do it backwards. My brain is not working like this at the moment. So I'm gonna waste a line, 0 to pi over 2. I could put the minus on the limits and swap them. Perhaps I should have done. Now it's too late. I wrote them. So let's move the minus on the top. So sec squared of x over 2. And I will reverse the limits and I will rewrite it as tan squared of x over 2. This will now go into a minus 2 tan of x over 2, and the 3 will go into a minus 3 dx. Next, complete the square on the denominator. 0 to pi over 2 minus sec squared of x over 2. I got my function of, I forgot to mention, we already there, we got some kind of perhaps arctan. I have no idea what's going to happen to this. Function of tan of x over 2 at the bottom and the right quantity at the top. But this, of course, I do not recognize until maybe I can go to an arctan or something like this. This doesn't look good at the moment. It's not an arctan because I got the wrong signs. Let's have a look. Let's complete the square first of all. Tan of x over 2 minus 1 all squared. So, and then I have a minus 1, minus 3, is minus 4, it's not arctan. I can go arctanches and arccoths and things like that, but, oh gosh, I mean, I don't remember a lot of the formulas from there. The logarithmic forms, that is. The best way for something like this is to go partial fractions for something like this. It's probably so we can all follow, because I'm doing a lot of things by recognition. I don't want to do things by recognition. These are partial fractions from this line. It's probably use a substitution. I'm going to actually use a substitution for this, so it'd be better for everybody. I'm going to use a substitution. U is this bracket here. So I'm going to write it somewhere on the left here. U is equal to the tan of x over 2 minus 1. My du is going to be a half sec squared of x over 2. The minus 1, of course, we dump it, dx. So my dx is going to be 2 over sec squared of x over 2 du. And the limits 0. What's the substitution there? Is 0, goes tan 0 is 0, it goes to minus 1. And the other one, the pi over 2, 90, 45, 1 minus 1, it goes to 0. So this is the substitution, so it'll be easier to see the partial fractions from there. So the 0 is minus 1 to 0. This, of course, will cancel from the substitution, so let's leave him. X squared x over 2, and this is now a u squared minus 4, which I will factorize on the next line to break my partial fractions, And what we'll get there, that the x is 2, so 2 over a sec squared of x over 2 and du. All right, so the sec squareds will cancel. Let's do a little bit of tidying all of this. We've got that 2. We got the minus 2. I'd swap the limits. Maybe I should swap the limits. I prefer the partial fraction like that because I can do them in my head. So this will go minus 1 on the top, 0 at the bottom. And I'm going to have a 2 over u minus 2, u plus 2 du. These are standard partial fractions, and a lot of us kind of like see what needs doing is plus is on the minus 2 and the minus on the plus 2, and it's the same number. We just have to make sure, is it ones? So u 2 is actually halves. Okay, so if we look at this now, it's a half u and sorry, minus a half u and a half u will cancel, and then we'll have, of course, if we look at this, half of 2, which is 1, minus half, which is another 1, so it's the 2 that we got in there. Okay, so by cover up, or actually I didn't use cover up there, it's kind of like another structure of these quantities, and I kind of guess the numbers and balance them. Okay, so this is now ready to be integrated. I've got the limits all there. So this will be equal to a half log of u minus 2 minus a half log u plus 2 between the limits of 0 at the bottom, minus 1 at the top. Factorize the half, write it compactly, u minus 2 over u plus 2. And then the evaluation limits there, 0 and minus 1. And let's put the numbers in and see what happens. A half minus 1. So minus 1 is going to give me now a minus 3 there. And minus 1 plus 2 is 1. So that's, of course, modded. So that's going to be a half log 3. And when I put my 0, 0 there and 0 there, it's going to be minus 2 over 2. Of course, modded is, of course, minus a half log 1, which, of course, is nothing. And therefore, the answer to this one should be a half log 3. I hope you found this useful. Okay, I've done 4 examples, and I hope you're not bored or you found it too difficult. And I just sincerely hope you got something out of this particular session. I will see you very soon.